If the last lecture starts from where we left in lecture 4.5, let us start in this lecture from where we left in lecture 5.1. I mentioned then that as far as drawing free body diagram was concerned, we might treat the object of concern as point particle upon which the forces were acting. As a result, as long as the forces acting on the object cancel each other, the object would either stay put or move at constant velocity as dictated by Newton's first law. However, if you have ever pushed an object before, a bookshelf for instance, you will realize that the world is not so simple. Despite of your trying your best to ensure that you provide force large enough only to encounter friction, the whole shelf may still topple. Having zero net force acting on the shelf does not necessarily guarantee that the shelf will truly be in equilibrium. The problem obviously lies on the fact that a bookshelf is not a point object. Real physical objects have shape and size, and forces may act on any part of them. If you think of the wheels and gears we discussed in the previous lecture, they are definitely not point particle objects. It does not make sense to talk about angular, tangential, radial, or center of rotation motion on a point object. So although an object may be in equilibrium as far as translational forces, that is, forces which cause the object to translate or to shift along horizontal and vertical direction, cancel each other, it may not necessarily be in equilibrium when rotational forces are concerned. To further simplify the discussion, we will only consider rigid body objects in this course. A rigid body means the shape and size of the object stay rigid regardless of the forces exerted. The applied forces do not deform the object. Now we need to come up with a more formal definition to describe this so-called rotational force. That formal definition is called torque, or for some of you who have learned this before, it also goes by the name moment. Torque is denoted using the Greek alphabet tau. Mathematically, torque is defined as force times radial distance from the axle where the force is applied times the sine of the angle between the orientation of the force and the radius. In plain English, torque is the effect of force when it is applied to rotate an object about a certain axle or axis. This definition of torque or moment caused it, as we went through earlier when discussing dimensional analysis, to have the same dimension and hence the same SI unit as work or energy. But of course, there are different physical quantities. They certainly carry different physical meaning, and because of that, you cannot just equate work or energy to torque. Also, to avoid confusion, we call the SI unit of energy joule, and we simply stick to Newton meter to call the SI unit of torque. The best and easiest way to understand torque is through the example of a man pushing a door open. We push open doors countless times on a daily basis that we do not even think twice how exactly we do so. But let's recall again the last time you pushed open a door. Replay that in your mind in slow motion. What do you see yourself doing? You will probably start by applying a force on the door. Typically, you don't even bother to reach for the handle. You simply push the body of the door itself probably some distance away from the hinge. And naturally, the direction of the applied force and the radial distance from the hinge form an angle. What you just applied on the door is not really force. Instead, you apply torque. Torque what swings the door open, not force. For you can apply a lot of force, but if you apply the force on the wrong part of the door, such as those parts nearer to the hinge, the door may not open. At least, it is not going to open easily. That is because, although you may apply great force, the radius is too small. In turn, the applied torque is too small to push open the door. In the extreme case, of course nobody does this, but if you try to open the door by pushing the axle or the hinge of the door, obviously the door is not going to open, no matter how much force is applied. The torque is zero because R is zero. Also, nobody opens the door this way, where the force is directed along or very near to the radius. The door is not going to open, or even if it does, it only happens after great difficulty of pushing the door open. If the person is strong enough, she or he may be able to tear the door away from the hinge, but the door will not swing open in typical manner. And that is because the angle between the direction of the applied force and the radius of the axle is close to 0 or 180 degrees, depending on which angle you are looking at. Either sine 0 or sine 180 degree is 0. Once again, last force does not necessarily translate to last torque. Enough with negative examples, this equation tells us how to push a door open in the most efficient manner. We stand furthest possible away from the axle to maximize R. We then push the door open perpendicular to the door itself in order to maximize sin theta, and we should not have any problem pushing the door open even with gentle force. Okay, so that's about torque. So how are all these related to our earlier discussion about whether an object is in rotational equilibrium? Well, just like when we learned earlier in lecture 5, if the net force acting on the object is 0, which means either no force acting on it or the forces somehow cancel one another, we state that an object is in equilibrium. To be very precise technically with the term, we should say that an object is in translational or linear equilibrium. In that situation, the object will either continue to move at constant velocity or stay put as far as center of mass motion is concerned. In light of our newly learned concept of torque, we can now say that for an object to be in rotational or angular equilibrium, the net torque acting on the object has to be 0 as well. In that situation, the object will either continue to move at constant angular velocity, remember we discussed angular velocity in lecture 4.5, or stay put as far as rotational or angular motion is concerned. You can think of the second equation as the Newton's first law in rotational dynamics. I didn't mention that torque is a vector quantity, did I? Torque is indeed a vector. Its magnitude is given by F times R times sin theta presented just now, while its direction is given by the so-called right-hand rule. As the name of the rule suggests, regardless whether you are a left-hander or right-hander, you still have to use your right hand. The idea is to curl our forefingers and stick out our thumb straight up like when we are appreciating somebody for his or her good work. We then curl our forefingers in the direction of the rotation, which naturally will cause our thumb to stick in particular direction. That direction is the direction of the torque. Interestingly, this orientation happens to be adopted by technical designs of any screws, bolts, and nuts in the world. If the curl of forefingers is aligned to the turning of the screw, then the thumb provides the direction where the screw is drilling through. For that reason, we always turn the screwdriver to the right when we want to put a screw in, and we turn the screwdriver to the left when we want to take a screw out, as seen from the head of the screw. That is always the case anywhere on Earth. This provides an easy way to remember the direction of torque. And once again, remember to use your right hand. If you use your left hand, you will get the torque pointing in the opposite direction. In conclusion, for an object to be in truly static equilibrium, that is to say it is neither shifting or toppling, both the net force and the net torque has to be 0. I will close this video with a very simple problem whose result we are likely familiar with, the seesaw or balance beam problem. 3 friends, Leon the lion, Chicky the cheetah, and Hippie the hippo are standing on the seesaw as shown above. Leon, or to be very exact with my term, Leon's center of mass, sits R1 distance away from the center of the beam. Chicky's center of mass is R2 distance away on the opposite side of the beam, while Hippie stands exactly at the center of the beam. If the weight of Leon, Chicky, and Hippie is W1, W2, and W3 respectively, what is the condition for the beam to be in static equilibrium? Well, we start by drawing the free body diagram of the beam. The most obvious forces acting on the beam are the weights of Leon, Chicky, and Hippie. The next forces to be drawn is the normal force that the stand exerts on the beam at the center. So that's it. Those are the forces concerned. Now for the beam to be in static equilibrium, the beam must be in equilibrium both translationally and rotationally. The former is straightforward. We have gone through quite a number of exercises on this. The forces must cancel each other, and from there, you can deduce the equation that describes the normal force on the beam. The latter is where we are to apply our newly learned concept of torque. For the beam to be in rotational equilibrium, the torque from the forces have to cancel one another. But you will soon realize that you do not need to worry with forces who pass through the center of rotation. Hippie's weight and normal force will not cause any torque. Just like when you are trying to open a door by pushing at the hinge, these forces will not produce any torque because the force is applied on the rotational axis. R is 0. What we need to be concerned of is Leon's and Chicky's weight. Leon's weight causes the beam to rotate anticlockwise. If you apply the right-hand rule, you will notice that the torque is pointing to you out of the screen. Go on and try to apply the right-hand rule and convince yourself that it is the case. Now, just like forces, we have positive force if it is pointing along positive x-axis or positive y-axis, and negative force if it's pointing in the opposite direction. The direction of torque can also be distinguished from its sign. Here we adopt the same convention as a sign in angular velocity. If the rotation is anti-clockwise, which means the torque is pointing out of the screen toward us, the torque is positive. Vice versa, if the force causes the beam to rotate clockwise, which means the torque is pointing into the screen away from us, the torque is negative. We can finally sum up the torque to get the net torque. Please note of the negative sign here. The condition for the beam to remain balanced is this equation. It is a result which hardly comes as a surprise. It essentially says that for the beam to be balanced, heavier objects should be placed nearer to the axle. On the other hand, we can lift and balance a heavy object using relatively small force if we have a beam long enough to make a lever. A lever makes use the longer arms to generate large torque from relatively small force to counter the torque for much heavier object as shown in this figure.